Hello networking enthusiasts. In today's fast-paced world of cloud-native applications, securing your Kubernetes cluster is more important than ever. By default, Kubernetes allows all pods to communicate with each other, leaving your application exposed to potential security threats like vulnerabilities, data leaks, or unintended interference between applications. Moreover, if a pod is compromised, an attacker could potentially access other pods or services within the cluster. This is where network policies come into play. They help you lock down your cluster and control exactly which pods can communicate with each other. In this video, we'll break down the basics of Calico networking policies. You'll learn how to define rules and restrict traffic, select pods by IPs, labels or services, and even define cluster-wide rules. Whether you're managing a small application or an enterprise-grade deployment, mastering Calico can give you the power to secure your Kubernetes environment with confidence. If you are ready to take your Kubernetes security to the next level, hit that subscribe button, give this video a thumbs up, and let's dive into Calico's network policies. The task at hand is to introduce firewall rules to segment traffic between applications running on our Kubernetes cluster. Let's say we have a full stack application that has pods running our frontend and pods running our backend and pods running our database. By default, all pods can talk to each other freely as the pod network is flat. What we'd like to achieve is to introduce firewall rules so front-end pods can talk only to backend pods, and backend pods can talk only to the database. What we don't want is the front-end to talk to the database directly, or the database to be able to connect to the front-end. To control communication between pods and other networking endpoints, there's a special Kubernetes resource called Network Policy. It gives you the ability to define rules that specify which types of network traffic are allowed to enter and exit a pod. Important thing to note is that the network policy enforcement happens at the layer 3 and layer 4 of the networking stack, meaning IP and port. Moreover, it's done at the pod level. While the network policy resource is available out of the box, the enforcement of network policies depends on the CNI plugin that handles Kubernetes networking. Today, we'll work with network policies provided by the popular Calico CNI plugin. Calico is not only a widely used networking solution for Kubernetes clusters, but also provides network security. Once you install Calico in your cluster, you can start using Kubernetes network policy resources to isolate traffic between pods. However, Calico offers its own extended version of network policies called Calico Network Policy. Calico's implementation includes additional features such as more traffic selectors, support for more protocols, policy ordering, global policies, and more. Let's start with some basics, just to get a feel on how it all works. We have two node Kubernetes cluster running Calico as the CNI. Our playground consists of 3 deployments, each with a single Alpine Linux pod. Deployment 1 named Alpine 1, deployment 2 named Alpine 2, and deployment 3 named Alpine 3. Let's create those deployments. Let's check if pods have been created. Okay, 3 pods are there, 1 pod per deployment. Now I will go to shell of Alpine 1 pod, then shell of Alpine 2 pod, and the shell of Alpine 3 pod. Let's add the bind tools package that we need to test DNS resolution later in the video. Here are the pods IPs. First thing I'd like you to notice that might sound obvious is that if there is no network policy defined for pods, then the traffic is allowed. Let me go to Alpine 1 and ping Alpine 2. Works. Now, let me ping Alpine 3. Also works. Let's define a network policy that allows ICMP traffic from Alpine 1 to Alpine 2 pod and blocks all other traffic. Here's a very basic network policy manifest. The API version is Project Calico version 3. The type of resource is network policy. Network policy applies only to a single namespace. The namespace it is deployed to. In our case, it's the default namespace. Then in the manifest section, we have the policy name, Then there's the selector. It's used to identify the pods that the policy applies to. We'll talk about selectors in a bit. For now, we'll put all. This is a special keyword that matches all the pods in the namespace. Then we specify the policy type. It can be either ingress, if we want to apply the policy to incoming traffic, egress, if you want to apply the policy to outgoing traffic, or ingress-egress, if you want to apply the policy to both incoming and outgoing traffic. If you don't want to specify this option, Calico will try to figure it out for you. As our policy type is egress, we need to provide a list of egress rules. Each rule has 4 basic properties. Action, that tells the rule what action to take. Allow the traffic, deny the traffic, or lock the traffic and continue to the next rule. Then there's the protocol. For example, TCP, UDP, ICMP, and so on. Depending on the protocol, we can also add additional parameters like TCP ports or ICMP codes. Then we specify traffic source and traffic destination. Source or destination can be matched by various criteria. In the first iteration, we'll match the traffic based on the IP CIDR range. To do that, we'll use the nets keyword and then provide a list of IP ranges. If you want to match a single IP, you simply specify the /32 as the mask. In this example, we have Alpine 1 pod IP as the source and Alpine 2 pod IP as the destination. Okay, let's apply that policy. Here you go. Policy is there. Let me try pinging Alpine 2 pod from Alpine 1. As expected, traffic is allowed. Few things you need to be aware of. Rules are stateful, so the return traffic is allowed by default. You don't have to add a second rule for the return traffic. If Alpine 1 initiated the connection, then the reply from Alpine 2 will get to Alpine 1. However, if we try to initiate the traffic from Alpine 2 to Alpine 1, it won't work as it's not allowed. Why is it not allowed? Network policies follow an implicit deny principle. This means that if a pod traffic doesn't explicitly match any of the defined rules in the network policy, then it is denied by default. So when a pod attempts to communicate, Kubernetes checks if there's a matching rule in the applicable network policies. If no matching rule is found, the traffic is denied. Implicit deny rule applies to all pods in the namespace, as we did put the all keyword in the global selector. If we put only specific pods here in the global selector, then implicit deny would be applied only to those pods, and the rest of the pods would have no policy. And like I told you at the beginning, no policy means traffic is allowed. Okay, we achieved our goal. Traffic from Alpine 1 to Alpine 2 pod is allowed, and all other traffic in the namespace is blocked due to implicit deny. To sum up, the network policy resource is available in any Kubernetes cluster by default. However, to enforce network policies, you need a CNI plugin that supports network policy, such as Calico, Cilium, or KubeRouter. If your CNI plugin doesn't support network policies, then defining network policy object will have no effect on pod-to-pod communication. Next, if you introduce a network policy, a default implicit deny rule will be created, but only for the pods that you target in the policy. Okay, where are we at? We have 3 pods. Ping from Alpine 1 pod to Alpine 2 pod works, and all the other traffic is blocked. Our policy targets all pods in the default namespace. It allows ICMP traffic where the source is Alpine 1's address and target is Alpine's 2 address. Let's delete Alpine 1 pod. A new pod has been created in its place. Let me try the connection from Alpine 1 to Alpine 2 one more time. The connection is no longer working. But why? The issue we are facing is that the newly created Alpine 1 pod has a new IP address. The pod IP is .93 now. If we look at our network policy rule, it expects a .90 address as the source. What to do next? Instead of matching by IP CIDR range, which is useful if you want to allow traffic to a specific network outside of the cluster, we can match by other properties like, for example, labels. Let's look at our Alpine 1 pod. It has an app equals Alpine 1 label assigned by deployment controller to all pods under Alpine 1 deployment. I have a simple network policy ready. Here, instead of matching by CIDR range, I'm using the selector keyword. I want the rule to allow traffic from pods with label up equals Alpine 1 to pods with label up equals Alpine 2. Okay, let's create the network policy. If we look at the newly created network policy, we still see it targets all pods in the namespace, but this time it looks for a source pods to have up Alpine 1 label and destination pods to have up Alpine 2 label. Let's go to Alpine 1 pod and try pinging Alpine 2. Works. Let's try one more thing. I will go to Alpine 1 deployment and change the number of replicas to 2. That will create one more pod in the Alpine 1 deployment. Let's enter the shell of that newly created pod. As you can see, it has totally different IP assigned. It was scheduled to run on a different Kubernetes node. I will try pinging the Alpine 2 pod. Works. What just happened? Every pod created as a part of the Alpine 1 deployment is automatically labeled up equals Alpine 1 by the deployment controller. This means we no longer need to worry about pod IPs, as firewall rules are now created based on this label. Every time a network policy is created or updated, or pod is created, deleted or updated, Calico evaluates the policies and generates or updates firewall rules behind the scenes. You are familiar with using labels to group your pods into services, identify which pods belong to which deployment, organize the pods by environment, team, schedule pods on different nodes. Now you'll use labels for one more thing: network policies. Let's dive a bit deeper into selectors. Apart from match all or match key value, there are other match operators. Moreover, selectors can be combined using logical operators to create more complex groupings. Let's list all the pods with up equals Alpine 1 label. Now let's add some more labels. I will add role equals frontend to the first pod and role equals backend to the second pod. Let's check if the labels have been assigned. Okay, labels are there. Let's analyze the following networking policy. If we look at the source selector, we'll see it matches two labels. Both of them need to be matched for selection. Up equals Alpine 1 and role equals frontend. There's only one pod that matches such criteria. That's the first pod from the Alpine 1 deployment. Same goes for the destination selector. It will pick a pod that has an up equals Alpine 1 label and role equals backend. Let's apply this manifest and test the policy. First pod has role equals frontend label. Let me enter its shell. Second pod has role equals backend label. I will enter its shell as well. I will ping from frontend pod to backend pod. Works. If we try the same thing the other way around, as expected, it does not work. One more thing. If we look at our manifest, we'll see up equals Alpine 1 in both source and destination. We can limit the scope of our policy to apply only to pods with specific labels. To do that, let's use the global selector. I will remove up equals Alpine 1 from source and destination and put it in the global selector instead. Such configuration is much cleaner. The policy targets only pods with up equals Alpine 1 label, where source role is frontend and destination role is backend. Let's apply this manifest. Okay, the global selector is there. The policy will apply only to pods belonging to Alpine 1 deployment. I'd like to show you two more handy operators: set operator and has operator. Here are our pods. Only pods from Alpine 1 deployment have a role assigned. Let's add a role equals backend label to the Alpine 2 pod. Voila! We have three applications: Alpine 1, Alpine 2 and Alpine 3. Only pods from Alpine 1 and Alpine 2 deployment have a role label assigned. Alpine 3 does not have the role label assigned. Let's say we want to permit ICMP traffic to the internet for all pods, but only if they have an assigned role. Let's see how such policy could look like. In the global section, we use the set operator. It matches all labels from a given set. So in our case, it will select pods with up equals Alpine 1, up equals Alpine 2, or up equals Alpine 3. In the source section, we are looking for any pod that has a role label set. We don't care if the role is frontend or backend or any other role. As long as the pod has a role label set, it will be selected. In the destination, we've put quad zeros. That's all IPs. Let's apply the manifest. Now the test. Alpine 1 has a front-end role set, so if I go to the shell and run ping to Google DNS, it will work. If we look at Alpine 2 pod, it also has a role assigned. So the ping command to Google DNS works. However, if we look at Alpine 3 pod, it does not have any role assigned. If I go to its shell and execute ping, it won't work. Let's sum up what we've learned so far. Calico Network Policy allows you to control what traffic enters and exits pods. Calico Network Policy applies only to pods in the namespace it was created. You can further limit the pods that the policy applies to by using a global selector. Traffic that does not match any rule is denied by default. You can select source and destination pods by CIDR range or labels. You can build more complex rules by joining your selectors using logical operators. You should use Calico network policies when you want to enforce network security rules on per namespace basis. This is useful when different namespaces need different sets of rules. What if you'd like to apply a cluster-wide network security rule? Don't worry. There's yet another resource called Calico Global Network Policy. It allows you to apply consistent security policies enforced regardless of individual namespace configurations. Let's see that in action. If I go to one of the pods and try to resolve google.com, it fails. In Kubernetes, the DNS resolution is handled by core DNS. That's in the kube system namespace. In front of core DNS pods, there's a kubedns service that directs traffic to those pods. Each pod has the IP of the kubedns service set in the resolver configuration. We can ping core DNS pods as we've created a rule that allows all outgoing ICMP traffic. However, we cannot connect to the DNS service on port 53 both via the service IP nor directly using the core DNS pod IP. We need a working DNS. Let's allow the traffic to kubedns service for all pods no matter the namespace. To do that, we'll define a global networking policy. Let me open the manifest. Oh boy, lots of things going on here. Let me explain it step by step. First of all, policy type is egress, so we target outgoing traffic. Secondly, the source is not present, so we target all pods. For the destination, we target the service named kubedns in the kube system namespace. Service matcher is very useful as it allows you to define network policies in terms of services while still enforcing the policy on the pod level. Let me reiterate. Service matcher will target the pods behind the service, not the service IP. Then the policy will be applied to the pods selected by the service. That's not all. There are two more things we need to mention. Global networking policy spans across all namespaces. Here in the global section, instead of using a regular selector, we use a namespace selector to target only specific namespaces. Project Calico name is a special label that's automatically assigned to namespaces by Calico. This label holds the name of the namespace, making it easy to select specific namespaces. If you look closely, there's a not keyword. We are targeting all namespaces except the system namespaces. The thing is, once we allow DNS traffic, an implicit deny rule will be created, blocking everything else. Hence, we exclude the system namespaces not to break the cluster. Let's apply the manifest and test if DNS resolution works. First, I will try to resolve an internal name. Works. Now an external name. All is good. By using Calico Global Networking Policy, you can enforce consistent security policy across multiple namespaces or across the entire cluster. By using Namespace Selector, you can target specific namespaces like, for example, block traffic between production namespace and staging namespace, or, like we did here, exclude system namespaces. By using a service selector, you can target pods behind specific services. How does network policy compares to a service mesh like Istio or Linkerd? A service mesh operates at layer 7, so it provides you with some advanced features like traffic management, retry, circuit breaking, service discovery, load balancing, authentication, and observability. However, service meshes introduce sidecar proxies within the pod that intercept and manage all network traffic to and from the pod. This additional layer adds overhead in terms of CPU, memory usage, and network latency. So, when you need a basic layer 3 network segmentation for security and traffic control with minimal overhead, you should go with network policies. If you need advanced layer 7 features, pick a service mesh, but it will come at a higher resource utilization, lower performance, and increased complexity. That's it for today. I hope you've learned something useful. In future video, we'll introduce network policies to a demo application, give you a high-level view of how all that pieces fit together. We'll also discuss segmenting your cluster with namespaces and policies, logging, rules order, sets, and how to apply network policies to ingress or load balancer. Until then, keep networking, keep learning, and stay safe.